Swayam Prabha. Digital India. Educated India.
So I'll define an allocation. So this is a division of my M in the discrete goods. So you have n agents. For every agent, you pick a subset of goods, and that good only, this collection, this subset of goods only goes to this agent. So in that sense, these are pairwise disjoints. You can't cheat and say, okay, I'll somehow sneakily give the same good to two of these agents. So these are pairwise disjoint subsets of goods. So again, if I go back to the previous example here, this is an allocation, this is a division, right? And when I say a fair allocation or a fair division, what I am looking for, what I'm trying to find is such a partition. So the first two goods get assigned to agent 1 and hence the subscript 1. These goods 3 and 5 get assigned to agent 2, hence the subscript 2. And this singleton G4 gets assigned to agent 3, hence the set A3, right? How many allocations can there be if I have m goods? Asymptotically, can you? It's slightly more involved than 2 to the m, but it's a good counting question. You have m goods, you have n agents. So this is one particular allocation. This is one way to divide it. Of course, I can also do something else. I can do this. So I can just G1 is A1. The first agent gets just one thing. This is A2. This is A3. Third agent gets nothing. That's another allocation. So, of course, there are many. Question to you is how many? What's the count of this? That's certainly a large number. There's a very nice closed form way to do this. N to the power m, right? So here's the way to count it. For every good, you just index the person who's getting it. So for good 1, you have n possibilities. One of the first guy gets it. Look at the second good. Again, there are n possibilities. You'll assign it to one of these guys. N into n into n, m times n to the m. Again, the point to appreciate is that for even reasonable values of n and m, this will be an extremely large number. So we are in a case where things are finite, but these are large. This is a substantially large number. Going through n to the m for even reasonable values of n and m is not an option. These will be exponential time procedures, if I actually go over all of them. Okay, so that's the definition of an allocation. For today, what is it that we are looking for? We are looking for such partitions. We are looking for ways to divide the goods into subsets among these n people. That's our objective, that's our sort of goal. So far so good? Okay. Now comes the important definition, and again this is sort of motivated by this bad example of two goods and a single agent, where the idea was, okay, there's a single agent that's causing trouble. So here's a definition, here's a solution concept. So it's a natural sort of relaxation of NV freeness. This was explicitly defined by Budish, and so note a major jump, like while NV free was sort of there starting from the 60s, this is a much more recent body of work. Even the definition I'm giving you is much more recent. There was some algorithmic work by Lipton et al. In 2004, but this specific definition came out of Budish's work. And I do want to emphasize that this is like, even looking at the right definition is a important intellectual exercise here, right? It's not like, okay, this is the obvious. And this will be apparent in one of the later lectures, probably where I'll try to discuss variants of this definition, and you'll see like how things quickly become very difficult. But for now, just look at this definition as some sort of a trade-off that you have to make to talk about NV freeness, to talk about fairness in this divisible goods case. So with that preface, here's the definition, and the concept is called, the notion is called NV free up to one good, and the notation is EF1. Yeah, idea is quite simple. Look, I will go for NV freeness, but I'll allow you the courtesy of removing one good from consideration. There is a single good that you can sort of remove out and achieve NV freeness. In particular, I'll say that an allocation, so this is the definition of this solution concept. So what is an allocation? Again, it's a collection of these pairwise disjoint subsets where each subset is assigned to one agent. So A1 goes to agent 1, so on and so forth. And I'll say that an allocation is EF1, it satisfies NV freeness up to one good, if and only if, let me write the definition and I'll pass through it. Okay, so the idea is I will deem an allocation, a division of these indivisible goods, to be fair, to be EF1 if the following condition holds for every pair of agents. So I'll look at every pair of agents, and then I'll say that, look, if it so happens that there is a good in AB such that the NV goes away once I remove AB from this good from consideration, then I'll say that the allocation is EF1. The order of quantification here is very important. Let me re-emphasize that. The idea here is that for every pair of agents, there exists a good G in AB. So if you change the pair of agents, in particular, if you change B to some other agent C, this good can change. So the idea is, again, A looks at its own bundle, says I have value VA, AA for it, so the left hand side. Now then A looks at someone else's bundle and says, you know what, if this other person B hadn't, if I remove this specific good G from the other guy's bundle, the NV vanishes, I do not NV B anymore. Again, so both the left hand side, the valuations are with respect to A, then I'll say it's EF1, I achieve fairness. So up to one good in the other guy's bundle, I have NV freeness. Okay, in the case of two agents, one good, do I have such an allocation? Yes, why? What is that? Yeah, so there's a single good, right? You have an empty set, your value for it is 0. The other guy has one good too. You remove that good, it's all, like both of us are paupers. The paupers don't envy each other. Fine. So, excellent. But a priori, this is a very trivial case and it's not obvious if such a thing exists. In particular, it's a good definition, but sort of the golden test for it is existence, at least existence in general enough settings. And like beating to the punchline, we will show that this thing exists for a very large class of valuations, a very non-trivial result, and we'll prove it the best way we know. We'll prove it by developing an algorithm that always finds such an allocation. So we'll not only prove that such a thing exists, we'll in fact develop an algorithm that efficiently finds such a fair division, that efficiently finds such a partition of these n things. Okay, yeah, just to sort of reiterate, be appreciative of the order of quantification here. This G does depend on your choice of A and B. So the idea is you pick any two, first make that choice. Once you have made that choice, there is a choice of the good in AB that gives you this inequality that says if you were to ignore G, the NB would go away. So, yeah, so there is a related notion, but the algorithm I'll discuss today is sort of from the work of Lipton. So, yeah, I mean, this is not a typo. The algorithm was for a related solution concept, but it was observed that this actually applies to EF1. So, it's not that you had an algorithm before and the solution concept came later. That would be something, but yeah, these are the sort of two important references here. Okay, learned a trick yesterday. Let's see if I can repeat it. Okay, looked easier on the. I do. This one? Nope. Okay, that didn't help. Perfect. Fine. So here we go. Here's the example we have. Let's try to see if this solution concept of EF1 exists here. And the way we'll try to get to it is actually by following an iterative process. So my goal now is, here's the setup. I have these three agents. I have 5 goods. Want to find a allocation, that is a 3 partition of this set of 5 goods. such that hopefully an EF1 is achieved. I already know I cannot achieve envy freeness. The question is, can I achieve this EF1? And again, armed with a theorem, I can like blindly tell you without even looking at numbers that such a thing exists. My goal though is to sort of do it in a suggestive manner, do it in a manner that will lead us to an algorithm. Okay, so here's an iterative attempt. Give me a So the kind of, I'll keep going down, but need more space. Let's see. Let's try it on a new page. Is this still visible? Like, or is this too small? And you have the numbers with you, so it's just a placeholder. The more real estate I have, the better. So it's like slightly smaller font, but I hope it's, I kind of know what's sort of there. So I'll index this. So this means the first iteration, the second iteration, and so on. And what I'll do is I'll sequentially go on picking goods, and I'll keep assigning it to agents, trying to move towards, or at least trying to maintain EF1. So I start off with a case where all three sets are empty. No one is getting anything. That's envy free, right? Excellent. So let's start with the fifth good. We'll sort of go look at goods in sort of the reverse order, and what we'll do is that, okay, agent 1 values it quite a lot. So the columns here in some sense are going to denote the bundles, the subsets of goods the agents are getting successively. So I'll pick, say, the fifth good and assign it to the first agent. So at this point, A1 looks like G5 and the other two sets are empty, right? Does this, I mean, I haven't allocated all the goods, but at this point of time, do I have EF1? Yes. Well, of course, no one envies these guys. They are having an empty set. If you look at 1, so say I look at the definition, invoke it for agent 3 and agent 1. So A is 3 in my definition, B is 1. Then there is a good G in A1, AB, which is exactly one good, such that once I remove it, the NV goes away. So this is indeed EF1. And again, as I said, this is a suggestive exercise in the sense that I will draw a graph which is called the NV graph. And the idea here is, fine, it is EF1, but I'll keep track of the NV I have in the system, and I'll keep track by drawing a graph where the edges sort of denote NV. Right, so at the first iteration, once the allocation, the sort of current allocation looks like this, G5 and empty sets, what I have is, so this is, say, agent 1. I have agent 2 and I have agent 3. So agent 2 and 3 don't envy each other, both of them have an empty pocket, but both of them do envy agent 1. So this is a directed graph where the vertices correspond to the agents and the directed edges literally point the envy. So think of it like as a room where you're sitting, you're looking at what everyone else has, and you're pointing to people with more than 2 arms maybe. Okay, I envy this guy, I envy this person, I envy you, I don't envy her, so on and so forth. So this is a very natural construct, a very natural graph, and you'll see that this is in fact going to end up as the protagonist of our algorithm. So this is, I'll formally define what this graph is, but all this means is I have vertices for these agents and they point with directed edges where they have envy. So as of now, this is what the graph looks like. This is what the envy scenario is. Okay, so the idea now is actually sort of intuitive. Look, at this point of time, agent 1 is the source of envy for both of these guys. What you would want to do is not aggravate the situation even further, right? You'd ideally want to say that the next good that I have to assign, let me give it to someone who is sort of not the source or not the end of some envy, right? So now I look at G4, and with this sort of guiding principle of not aggravating envy, what I'll do is say I just give it to A4, I give G4 to the second agent, right? So it's an arbitrary choice. I could have given it to both 2 and 3, but certainly giving it to agent 1 at this point is a bad idea, because then I would have aggravated the envy. It's a intuition, it's just a rule of thumb. We will eventually get to a formal algorithm and proofs, but let's work through this example. So I pick G4, and in the second iteration, my scenario looks like this. So A1 is just G5, A2 right now is G4, A3 is still the empty set. Is this EF1? I've already told you one such exists, and I'm doing this exercise. You don't even have to, you can just wake up from your sleep and say yes. These are rhetoric questions. But yeah, is this EF1? No, don't care. New Zealand is more important. India, New Zealand, yeah. That makes 2 of us. It is, right? I mean, if you have singletons, it's actually a moot definition. You just remove it and you'll get it. So this is EF1. Hope everyone is convinced of that fact. So, okay, having ignored that question, let me ask you, so at this iteration, so I have 2 right now, what does this graph look like? Is it going to change? Note that this graph represents envy among agents. What is that? Perfect. So agent 2 still continues to envy agent 1. Note that this graph is about envy. Why is this? Because for agent 2, this G5 is of value 1500, while what it has currently is of value 20. So looking at these 2 numbers, there is still envy between 2 and 1. So that edge certainly does not go away. However, a new edge pops up, right? A3, poor guy, still hasn't received anything. So this is where we stand. And again, let's follow our nose of not aggravating envy. Let's look at the next good in the sequence and give it to agent 3, right? So following the principle, yes. Well, okay, let's follow a convention. So right now, yeah, you're right. Perfect. Yeah, of course. Okay, so someone at least is paying attention besides me. Okay, so that's what the envy graph looks like. There's a very nice property that will continue to hold, which is that I'll always have a good option to allocate the next agent. And if once we appreciate that, we actually have the algorithm in its entirety. But as of now, it's kind of the next good is sort of obvious to assign in the sense that we do not want to aggravate envy. Giving the next good to either of agent 2 or agent 1 will in fact contribute to that. There's already envy towards agent 1 and 2, so let's not further this. let's go to agent 3, who no one is envious of. Okay. Fine. So let's speed things up. So what does the NV graph look like now in after the third iteration? So agent 1 is set for life. Agent 1 has lucky draw 1000. Okay, those notes are banned, but still good to go. Decent amount of money in the bank account, not going to worry ever. But let's kind of figure out for the other guys, like if something gets resolved. So when I say NV, I actually mean the inequality is strict. So at this point, note that agent 3 reaches some amount of satisfaction in life, in the sense that for agent 3 all these values are 10. So it will stop envying both agent 1 and agent 2, right? There's no envy. I mean, I have 10, you have 10. There's no source of envy. Fine. What about agent 2? Will agent 2 sort of change its mind? No. Look at agent 2, right? So whenever you're looking at it, agent, you have to focus on a row. Right now, agent 2 has good 4, right? Agent 3 has good 3. So from agent 2's perspective, if you just focus, it has 20, the other person has 15. So there is no envy. So this is what the graph looks like. Okay, again, singletons EF1 holds trivially. Fine. So I have G2, and again the point is I can give it to both 2 and 3. This will not aggravate envy. Why? Because neither of them are being envied by anyone else. So let's make a choice, and let me assign this to G2 to this guy. So now what is the envy graph going to look like? Agent 2 now starts envying, because if I look at from agent 2's perspective, i.e. from this row, this G2, G3, the bundle that is with the third agent is of value 30, while its current allocation, which is G4, is of value 20, so this edge comes in. Okay, so let me stop and ask you a good question. And if you answer this, tell me you're on the right path. I'm looking at this NV graph, right? If I want to find an agent who's not envied by anyone else, what would that agent be in this graph? As in this graph theoretic sense, what is that agent going to satisfy? What is that? Outgoing or incoming? Perfect. It will not have any incoming edge, right? I mean, you are at the bottom of the food chain if no one is pointing at you in this NV sense. So currently if I'm looking at iteration 4, who's that agent who's not being envied by anyone? It's agent 2, right? Said in a graph theoretic manner, this is a source vertex. In a directed graph, a vertex that does not have an incoming edge, it's a source vertex. Fine. So the rule of not aggravating envy in that sense corresponds to giving the good to an agent that's a source vertex in this NV graph. Okay. Right. So what do? I have one good left. I will now assign it to the current source vertex, which is agent 2, and this is where I land up at. Fine. Now let me ask you, is this EF1? So I've allocated all 5 goods, right? Is this an EF1 allocation? Okay, what is that? Okay, still NVs, that is, let's check that. So agent 1, agent 2 has these two goods, so its current value is 25, whereas agent 1 has, from 2's perspective, this 5 is quite, so the graph stays as is, it's the NV graph, right? So even if iteration 5, this is the scenario, fine, and so these two edges stay. So of course I am not going to ever eliminate NV, because the good 5 will always sort of result in that. I am after EF1. So my question is, with like, let's see if agent 3 envies anyone. So G2, G3, which is 30, and so yeah. So agent 3 is not envious. So NV graph looks like this. But my question to you is that this is a final allocation. This is A1, this is A2, and this is A3. Is this EF1? If you are asked such questions in a classroom, the answer is obviously yes. Doesn't matter what the subject is, doesn't matter who. Yes, I mean, why else would I? This is not a trick. Yeah, I'm not. Yeah, better things to do, right? So answer is yes, and this would require, like, if you want to do it following the definition, you'll have to look at all the cases, like look at all pair of agents, identify one good that sort of does it. But let me actually give you a succinct argument of why this is EF1. So indeed, this is an EF1 allocation. And here's my argument that it is an EF1 allocation. The argument is this: every time I assigned the good, I assigned it to a source vertex in the NV graph, right? So I followed the sort of my rule that so this graph was the NV graph. It dealt with actual NV. And okay, of course I will at the end have edges in this NV graph. I cannot remove NV, but this is the principle I followed. The principle actually stemmed from the fact that I did not want to aggravate NV. My claim to you, and once I prove this I'll stop, or even better, once you prove that to me I'll stop, is if I follow this rule, fine, I am always going to end up with an EF1 allocation. So it's not obvious, and this is sort of the crux of what we'll discuss next, that there is always a source in this NV graph. But say you were lucky, as in this example, that at every time you had to assign a good, there was, by luck, say, you had a source vertex, i.e. you had a agent that no one else envied. My claim to you is that if you have such an agent and you assign the next good to this person, to this vertex, to this agent, you will continue to satisfy EF1. Why is that? Perfect. Then note that once I assign this good, modulo this set, every other set continues to be the same. Right, so when I went from here to here, G1 was assigned to, only G1 was assigned, every other sort of set continued to be the same. I'm never removing something, right? These are irrevocable decisions. I give it to you, it's yours. Yeah, blessings. So the point though is that, so say the source, let me write this argument formally, and I'll, so again, when we prove the algorithm, I'll circle back to it, but I do want to appreciate why. So say source is I. So at this iteration, the source was agent 2, because no incoming edges. So you had AI, the set current bundle, which you update. So this you updated it to be like AI union G. So the next good G, you gave it to this guy. Now look at any other agent J. This guy's bundle stays as is. This G5 continue to be the same, A3 continue to be the same. So now, but note that before the update happened, from J's perspective, I had this inequality. Why? Well, I was not the source of NV. So obviously for every other J, there was no NV. Hence, I was the source. So for all J, this inequality held true. But that's it, right? Now, after the update, if I look at Vj, Aj, so Aj remains unchanged. So this is the new AI. Right, so the good that I assign next, I remove it, I get the old AI. So this inequality here exactly translates to this inequality here. I have updated AI, so like don't read it without this update thing. If you want, you can put a superscript to timestamp it, but that's the idea. Okay, perfect timing. If there's a question, I'll answer it. Otherwise, with one more observation, I'll claim to you that this actually gives me quite a general algorithm, but the dogma that I'm following is always assigned to source. It's a charitable idea, right? The poor guy, no one envies this one. So okay, next one, have at it. Okay, can you give me a directed graph where there is no source? Cycle, right? So in some sense, we just got lucky here that we always ended up with a source. What I'll prove to you in the next lecture, that we can always we make our own luck. We'll always ensure that I'll have a source. In particular, I'll make my NV graph acyclic. Okay, fine.